So page 12. We have, is this an increasing or decreasing function? Without even, you did the homework, I'm hoping, right? But cover it up and just look at it like, is this increasing or decreasing? Increasing, how do I know it's increasing? Because, just because b is greater than 1, right? This number right here is greater than 1, boom, it's going to increase. So I want you to do two things. Out of all the functions, I want you to narrow down what kind of function is this? Exponential, right? So we are in exponential territory, and you can do this sketch, like to kind of position yourselves, what's happening here. T stands for time in hours, and A, whatever goes on the y-axis, is the area. Okay, and because it's increasing, we know that it's going to start somewhere here and go up from there. We don't know how aggressive that increase is going to be, but it's going to do this in general. Okay, can this be right on the origin, guys? Can it be right there? It can never touch the x-axis, right? There's something called the asymptote, right? It's right along the x-axis, so it can never be on. So if you do that, you're going to lose marks. So when you graph it, please make sure it's off the x-axis. It's like somewhere above it. Remember, there's a word problem, so we don't care about this part. This part is not included. It's time. Time is positive, so don't worry about that part. Okay, so we've got that figured out. Let's enter it into our calculator, and let's make it appear. Okay, so 0.01. What is that? That 0.01 is our y-intercept, actually, right? It's really close to the origin, but not quite. 1.0968 to the power, right? You use the hat button and you press X. I'm going to graph it. I really don't see anything. So I'm going to use the features that this calculator has. I'm going to try Zoom Standard. That's my go-to to kind of figure out what's happening. And it seems like it's on the x-axis. Something is wrong. Something is not good here. Let's try Zoom Fit. There you go. Zoom Fit is letting me see this thing. I'm happy with this part right here, so we're good to go. Okay. It says here, make a graph of the growth over the first 72 hours. So that's interesting, right? So we're going to grab our ruler. I can give you a grid. So A is going to go right here. So try to make sure you go time in hours. It's so important that you don't lose marks for these little things. Area in centimeters squared. Okay. So there we go. What about my scale? What's up with my scale? What should I? It says for the first 72 hours, right, along the x-axis. So I'm going to try this. 10, 20, 30, 40, 50, 60, 70, 80, and that keeps going. So I'm basically going to use a scale of 10, go all the way up to 80, but what about my y? What about the y? I don't know. I'm going to do some investigating. I'm going to figure out at 72, how high up the y-axis am I? Okay? Because I'm told there's a stop there. So I'm going to go second, trace, value, x is equal to 72. What's y equal there? Try it. Because you're going to have to adjust your window most likely. I'm going to give it a try. Second trace value, 72. It says, can't do it, invalid. Attempted to use the variable or function where it is not valid. So I can't see it. So I'm going to change my window. I'm going to quit this, go to window. But the x max should be what? At least 72. I'm going to go 80. And my y min, here it is. I'm going to change this. I want to see a little bit into the negatives. But look at this. Look at how small these numbers are to begin with. So I'm going to go negative 0.1 or something like that to not see too much into the negatives. And I'm also going to increase the Y max that is currently in there. What should I change it to? I'm going to go 0.7 or something like that. Let's try that. Beautiful. So I'm going to try that. Second trace 1 again, 72. It's still not on there. Look, it's 7.74, but somehow I managed to get an answer out of the calculator. So I'm just going to be like, thank you very much, right? I appreciate that. So that is my Y value that I need to account for. So the 0.72, 7.75 has to be on this graph. So I'm going to go up to maybe 8 along here. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to label every second one. There we go, 2, 4, 6, 8. So I'm going to use my ruler to help me out. 72 is right about there. This is the 7 mark. 7.75 is right about there. So I think that's where the dot goes. Where am I along the y-axis? I can actually figure this out. Y-intercept is 0.01. It's a little bit, it's small, right? Like, how do I know this? If you're saying, where did you get that from? If you want to highlight, I'm just going to go to my equation and just say I got it from here. Whatever that number in front, we call that A, right? That is immediately my y-intercept. So yes, this is so close. It's almost not fair to have to graph that one. And this is technically all you need, but what I'm going to do is I'm going to ask you to figure out, grab another point somewhere along the x-axis. Let's maybe do 40 and figure out, can we have another point on there somewhere? Choose another point. I'm going to do that. Choose another point for the graph. I'm going to go second, trace, value, x is equal to 40. And y is equal to, I'll figure that out, second trace value 40. That is 0.4, 0.40. So you got to go to 40, 0.4. If this is 1, this is 0.5, 0.4 is just below it. So we're going to go right there. So this just helps you now to make the curve more realistic. So I will go to that point, and then as you can see, there's like an explosion where it just grows a lot faster after a certain time frame. So anything it grows exponentially grows really fast after a certain time. So population, right? Global or world population is growing exponentially. COVID cases were at some point growing exponentially. It was just like way faster. Like, it's not a straight line. It actually goes curve, and then faster, faster, faster. It just keeps going even faster after a certain point, right? So there we go. We stopped there because that's 72 hours right here. 72, 7.75. You don't have to label it, but then you know what did we do. So we basically came up with one reference point, which was given to me by the question. It says, hey, for the first 72 hours, please. And then I chose another point to help me out, just to help me out, because I don't know, is it going here? Is it going further out first and then shooting up what is happening, right? So there we go. So B, determine the area covered in 40 hours. It's asking me, after 40 hours, what is the area covered? Okay, that's what it's asking. Hope you can see that. Let me just bring that up a little bit. So we got to go second trace value. X is equal to 40. Y, we're going to figure that out. I'll just give you the answer for this one. It's 0. Oh, I just found it. It was just coincidental. So it's 0.40 centimeters squared. If you slap on the unit on that, you're good to go. You found the area that is covered in this case. C, how long will it take for the area covered to increase to 1 centimeter squared? In this case, it's asking you how long to cover 1 centimeter squared, right? So when you have the y value, we go y2 is equal to 1. Second, trace, intersect, and let's go ahead and find our x value. This way, I try to make it appear on the screen. Let me just do this real quick. 1. Y is equal to 1. What's happening? Oh, my Y max. I'm not seeing. My Y max is 0.7 and I'm graphing at 1. This should have been changed to 7.75 or 8 anyways. I'm going to change my Y max to 8. Run it again. And there it is. That's the intersection I'm interested in. So when things aren't happening, you need to kind of see what's happening here. Is my window off? What is happening? So this is 49.84 hours. And because hours or time in general is continuous, we are okay to state it in as a decimal. That's how long it would take. And D, the equation will no longer be accurate after 72 hours as the bacterium will have used up the available nutrients by that time. So it's almost like a limiting factor. If you're in biology, you've probably talked about that, right? Things can't just grow indefinitely. There's things that limit your growth. Given this information, state the domain and range in this context. Because I'm restricted in time, I can't just grow indefinitely. This is from 0 to 72. That's the only time this is valid. If you want to go set notation, you have to use the variables that the equation given uses. So you can go 0, t, 72 like that. For my range, what's the smallest area to be considered here? It's at the y-intercept, 0.01, all the way up to, what's the greatest area that I'm covering here? 7.75. Or, if you want to do set notation, you got to use A in this case, capital A. That's how you come up with your domain and range. E, this one I would really want you to know how to do. It's actually not that bad. Determine the doubling time of the bacteria. We will let y equal to 2 times starting population. Starting population or amount. I will go amount in this case. Starting amount. So we're going to let y2 equal to 2 times. We started off with an area of 0.01. So 2 times that is 0.02. You find that intersection and you've got yourselves the doubling time. How long does it take to double what I had? You know what? I want to really make this point. So I'm actually going to start with the equation here. This is as easy as just saying, you know, whatever is in front here, that's my initial amount, you double that, and then find the intersection, you get yourselves your doubling time. So I'm going to let y2 be 0.02, graph it. It's going to be hard to see, right? It almost looks like it's on the x-axis, but it's not. Second trace 5, enter, enter, enter. There we have it. Time is 7.50, right? Hours. Go ahead, guys. Yeah, so yeah. 7.5 hours is your doubling time. What is doubling time? If I ask you, define doubling time within this context, what does that number mean? That every 7.5 hours, 7.5 hours, my population is going to double, right? So if you have 1, it's going to be 2. If you go, the next doubling time would be from 2 to 4, right? And that's happening every 7.5 hours. See you, Vince. Coral Fest today. All right, let's go to the next one, which is a decreasing scenario. After a cup of hot chocolate is left on the table, the number of degrees above room temperature of the hot chocolate is given by this equation. And I'm just gonna say some of these questions are worded very weirdly, and I want you to learn to read carefully. Okay, what does it say? Even like if it's level of water, what is it with respect to the ground, with respect to the rock? What is it? It's the number of degrees above room temperature that we're talking about here, and that is my equation right there. Now, this is A, and this is B. So my y-intercept, just by looking at it, will be 0, 68, 28. B is less than 1, right? It's between 0 and 1. So it's decreasing. I'm losing every period. I'm going to lose something, right? So in this case, what you expect to see is you're going to start higher up the y-axis, and it's going to go towards your x-axis like that. That's what we expect to see here. So let's type this in and make it appear on our calculator. Sorry. Wakey, wakey. There you go, 68.28. Use brackets instead of times. 9, 3, 2, 1. Close the brackets to the power of x. I'm going to hit graph. Oh, I actually see something, right? And it's exactly what I expected. It's starting up top, coming down. Let's start zoom standard. I'm going to try zoom standard. I'm probably not going to see anything. No surprise. And now I'm going to try zoom fit. If you do zoom fit based on what you're currently seeing, it's going to try something. It's not going to be the best view. So I'm going to go zoom fit now. And there you go. And remember, it doesn't know it's a word problem. So that's why it's also including negatives here. But this is a very good starting point. Now I'm going to trim my window a little bit. My x-min, I'm going to go down to like -1 or something like that instead of -10. My x-max, I'm going to increase that a little bit as well. My y min, I do want to see the x-axis, so I'm going to go -2. So the y mins, the x mins, I go negative right away. And let's try this. Not bad. So I see what I need to see so far. It's never going to cross the x-axis, so you can chase it all you want. You're just not going to get there. So let's leave it for now. Let's see if this will do the trick for us. Make a graph of the number of degrees above room temperature as a function of time. So let's try that. How would you graph this? These ones are actually tricky because we haven't seen these functions very often, but we know what it's supposed to look like in general. So let's do our x and our y axis. And we have what? M. This is temperature above room. Okay, that's what we're measuring here. How many degrees above room temperature are we? And it's in degrees Celsius. Okay? And the y-axis I'm wrong, right? It's a mistake. You notice that? This variable is my x variable, and m represents the time in minutes. So my bad. I'm making sure you're awake, because you're supposed to pay attention. You stopped me, right? Sorry about that. I go off my script all the time. I don't always look at my answers to make it a bit more real, right? Otherwise, you're like, oh, he gets it right every time. No, I don't, right? I don't. Time in hours. And this is temperature above room. And it's in degrees Celsius. You got to have your units in there if you want to get the full marks. Time in minutes, as I was saying. I was actually looking at this one, but this is the one we just did, which is time in hours. I have to look at this page right here. Okay, anyways, we're doing good. Let's write down our equation here, 68.28. I didn't do that on the other one. I remember now. But just write it down so you don't forget. There it is. Because this is a decreasing function, I know I start somewhere up here, and then it's going to go this way. And I know my y-intercept, which is 68. So I'm going to go up to 70. 1, 2, 3, 4, 5. That's 50. 6, 7, 8, 9, 10. So this is 100. Why not? I went all the way up to 100. 68 would be right about there, so I'm going to make a dot along the y-axis, and I know it's doing this. And that's where the problem lies. How far do I show, Mr. Dirksen? The problem will tell you, okay? I will tell you. There'll be a hint. You can't just guess. But let's try. What did I do on my key? I went to 50. Why did I go to 50? Just because. So I didn't tell you enough here. So let's just, basically this. Graph it. If I don't give you enough, just graph it and make this line be as close as possible, or a bit closer at least, to your x-axis. So let's go all the way up to 100 in our x-max. And then you see that, hey, it's going much closer here. So let's try to find a point somewhere here. Second trace value, I'm going to try 80. If I type 80, I'm super close to the x-axis. I don't like that. I'm going to try something a little bit closer here. So let's try 50. Second trace value, x is equal to 50. That's 2.03. That I can make work. So I'm going to just write that down here. These are just points to graph, okay? Try x is equal to 50, for example. I got y is equal to 2.03. 50, 2.03 is a point that I'm going to try here. So that means I need to go 10, 20, 30, 40, 50, 60, 70, 80. I'm going to continue that. So 20, 40, 60, 80, just like that. At 50, I'm at 2 something, so I'm really close. Okay, so technically, we can just go ahead and graph it there. It doesn't tell us that it stops. Okay, but let's think about this. If I have my coffee, I drank it already this morning, but if I left my coffee in this room, and it's 18 degrees in this room, which is cold, okay? What's going to happen to the temperature of that coffee eventually? It's going to go down to what? 18, right? Like eventually it's going to be whatever the room temperature is, and it's not going to drop past that, right? So keep that in mind. Let's keep going. That's A. So B is determine how long it will take for the temperature to cool to 20 degrees above room temperature. How long? So how long will it take to be 20 degrees above room temperature? So we need to use y2 is equal to 20, second, trace, intersect. So let's go ahead and find that. There we go, second trace 5, enter, enter, enter. 17.46. X is 17.46 minutes. And because time is continuous, decimals please, okay? The only exception is like on the test there was like what year, and which year was it the lowest usage of screen time. Then you have to round, okay? Okay, so C, what is the actual temperature of the hot chocolate in 30 minutes if the room temperature is 20 degrees? I want to say this. For the actual temperature, we would have to go room temperature plus degrees Celsius above room temperature. That's like the actual temperature of my hot chocolate. The room temperature, we already know, it's 20 degrees. We need to figure out this, okay, after 30 minutes. So when X is equal to 30, I want to know how many degrees above room temperature am I at 30 minutes, okay? So that second trace value, X is equal to 30, let's figure out what Y is. Second trace 1, X is equal to 30. That's 8.28 degrees Celsius. Remember, this is always temperature above room temperature. That's what we're finding every time we're finding Y. Because it wouldn't be hot chocolate if it's 8 degrees Celsius, right? That'd be not a pleasant drink, right? So then it's the room temperature is 20 degrees Celsius plus 8.28. So it's the actual temperature of this drink. The actual temperature of the drink would be 28.28 degrees Celsius. So it's a bit of a twist here. It's not just find the Y. You have to do a little bit of extra work to answer this question. Okay. D, what is D asking for? This is also important. Okay, so the doubling time that we did earlier and the half-life is very important for you to know how to do that, because it's almost guaranteed that I'm going to have that on the test, guaranteed. Okay. D is asking what's the half-life for the degrees above room temperature. Half-life, what we need to do is we need to let Y2 be initial divided by 2. So So whatever your initial temperature was, we need to divide that by 2. So what is our initial temperature? 68.28 divided by 2. Because remember, temperature is going to drop. That's why there's no such thing as doubling time on a decaying function, right? There's no such thing. It's half-life. You're dropping every time. So 68.28. I should be able to do this one without calculator, but I don't want to make more mistakes today. Enough is enough, right? So we let y2 equal to 3414. So y2 is 3414 second trace intersect. This is always going to be a second trace intersect scenario when you do doubling time and half-life. It's going to be like that. So let's go ahead and do this. You should follow if you can. I'm going to graph this thing. My window should be okay. There it is. So second trace intersect. Get a little closer to it. Enter, enter, enter. And that's 9.59 is my time. That's what I'm after. X is 9.59 minutes. So, you know, after 9.59 minutes, your drink is going to go half of what it was before, every time. That's why it cools off so fast, right? When you leave it out and you don't drink it right away, your coffee or whatever, because it's exponential. It's like an exponential effect, in this case, decreasing. Okay. All right. I think that was my plan. That was it for this. I think what I will do is one more